Hooray! How's everybody doing this morning? Going to give people about a minute, and then we will start today's fascinating lecture on reviewing for celebration number 2.
K is equal to W.
All right, so while people are joining, let me do a little screen share and give you some information on celebration number 2. Dun, dun, dun. Let's use draw red. Okay, so celebration number 2. Is tomorrow. Couple quick things. There will not be a lab tomorrow. I am not doing a lecture tomorrow. The celebration, just so you know, will be 3 hours max. So from the time you start it, you will have 3 hours to complete it. That should be plenty of time. It is basically 25 questions. And some of them are going to be multiple choice. And the multiple choice can be both conceptual and just the short problems. And then there will also be a couple of some problems where you have to input the answers. So you're actually going to have to type out what is the value of, the acceleration in meters per second squared, or the potential energy, or something like that. Be clear, it's going to cover chapters 8, 9, 10, and 11. Today I'm going to go through sort of each chapter and let you know what is the most important material. It will be approximately evenly covered. So 25 questions, 4 chapters, about 6 questions from each chapter. And in terms of what is allowed, this is basically open book, open notes. The only thing you can't do is no internet searches. Now, your PLC that's due today by midnight is basically just creating a 1-page cheat sheet. Even though it's open books, open notes, if you don't have some kind of organized cheat sheet prepared, it's going to make your life much more challenging. And in fact, when I first started teaching at Cabrillo, I used to have all of my tests open notes, open everything. And in fact, I had students that said that was too much. It was a lot better if they were forced to actually condense all of the information into a cheat sheet. So it is open notes, it is open book, basically everything except the internet, but you're going to be much more likely to succeed if you have an organized, nicely created 1-page cheat sheet. A couple other things, it must be completed. So must be completed. And by completed, meaning not just started, you have to have everything finished by 11:59 p.m. Pacific Standard Time. So basically California time. So do not start this any later than 9 o'clock because you may not have time to finish, even though I think 3 hours is more than enough time. Couple things, I'm trusting people not to share answers with anyone else. You'll see, just like the quizzes, this is going to be relatively straightforward. I'm not going to hold people to the same standards I did before we went online. And so you'll see the questions in terms of the problems are relatively straightforward. I did not post my old celebration from last time just because I don't think it's relevant. The problems are much harder. And I included chapter 12 in the old celebration that I'm not doing now. So what I want to do is, before I sort of review each chapter and tell you about the most important information, I want to just stop for a second, open it up for any just general questions, not about the material, but about anything involving doing the celebration number 2 through mastering physics or anything like that. Could you post the old celebration anyways? Yes, I will do my best to post it tonight. Just one issue, I don't know if I shared with you, but I have my daughter also, and so she's not in school. And so literally when I am not lecturing or in office hours or something like that, I'm homeschooling her. So I have her all day today. I'll do my best to post the old, you know what, if I don't have time to post the old celebration, at a minimum, I'll email it out to everybody, just because it's a lot faster for me than trying to upload everything to Dreamweaver. So I'll get you those old celebrations today, but like I said, they're not really probably going to be useful for this particular celebration, because I'll show you some of the sample problems. They're at most a couple steps, a couple relatively easy steps, nothing on the order of the kinds of problems that you saw on the first celebration. Anyway, do you have any advice on how to prepare for 4B? I don't. And just so you know, I am now, we're being asked to prepare for the possibility of the fall semester being online. And so there's a small possibility that this is going to continue until the fall semester. And one of the things we're trying to figure out is how the hell are we going to do labs? It's looking like if the fall semester is online, they're going to let the instructors go into the labs and film the labs, but there still wouldn't be any live labs. So at this point, the answer is no. Things are just so crazy. I don't have any great advice. Oh, actually, I do. One thing. Let me just show you one thing I can share with you. Let's just go to, so again, this is nothing completely relevant for right now, but if you go to open link in new tab. So can everyone see this sort of physics 4A homepage? Somebody give me a thumbs up or yes?
Yeah, looks
Yes.
Okay, so if you go to the website address and you just change the 4A to 4B, what you have is my old physics 4B website from the last time I taught it. And kind of like before, what I have is I have homework solutions, I have old quizzes, I have old quiz solutions, I have celebration reviews. I'm not going to be teaching it in the fall, so you know, the material might be at a slightly different level, but in terms of preparing for physics 4B, this site will remain open as long as Cabrillo doesn't make me shut it down. Even if I do, I'm going to upload it to joemccullough.com. I would say that if you're taking physics 4B in the summer, or I'm sorry, in the fall, check out my website, start reading ahead, especially if it's going to be done online. Okay, how do we turn in PLC number 11? I created, let's just do one more screen share. Bum, ba, da, bum, bum. Document sharing. So in Mastering Physics, I created just new folders for PLC number 11 for the 8 a.m. lab, 11:15, 2:45. So again, it's just a one-page cheat sheet just to help you stay organized. And then just like before, take a picture of it or make it a PDF and just make sure you rename it before you upload it to Mastering Physics. Great questions. Any other questions before I go through and just talk about each chapter and what's important in terms of the upcoming celebration? All right, let's go through sort of each chapter one at a time. So chapter 8, if you remember, was basically just, and just in terms of going through these, I'm just going to sort of go through the important stuff, things that you can skip. So chapter 8 was really just Newton's laws dealing with circular motion. And so what we covered in chapter 8 was basically uniform circular motion. And this is when you're moving at a constant speed in a circle of radius r. So uniform circular motion basically means the speed is not changing. And non-uniform circular motion, this is when an object is both changing direction and changing speed at the same time. Some of the big equations from this chapter. So one, let's just talk about things you don't need to worry about. I did not go through this whole RTZ coordinate system. You don't need to worry about that. I didn't really talk about things in orbit, so don't worry about that. Projectile motion, we've covered this in other chapters. I didn't really talk about this in terms of chapter 8. And then in terms of these RTZ, blah, 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 didn't do that. So really the big important things in this chapter is really just looking at Newton's laws in terms of circular motion. The things to keep in mind for something that's moving in a circular path is we know the acceleration. The magnitude is always v squared divided by r, and the direction is towards center of the circular path. So what's going to happen and basically is you're going to have the sum of the forces equals ma. Remember that this is really a vector equation. I could do the sum of the forces in the x direction equals max. Sum of the forces in the y direction equals may. The only real difference is in one of these directions, either the x or y direction, the object's going to be accelerating because it's changing direction. And we know that acceleration is given by v squared over r. So the net force is always going to be pointing towards the center of the circular path. And keep in mind, even though the magnitude of the centripetal acceleration doesn't change in uniform circular motion, the direction does constantly change. So uniform circular motion is not motion under constant acceleration because the direction of the acceleration is changing. So in terms of uniform circular motion or non-uniform, the big thing to know about this is really conceptually. If I asked you for the total acceleration of an object, you should be able to tell me what quadrant the total acceleration is. So for example, let's do a little clicker question. Do I have a clicker question for this one? Yeah, so just a quick little example. Clicker question 3. A ladybug is clinging to the rim of a spinning wheel, which is spinning counterclockwise, so spinning in this direction, very fast and slowing down. At the moment shown, what is the approximate direction of the ladybug's acceleration? So the ladybug is right here. We know this thing is moving counterclockwise, but it's slowing down. And the question is, what is the direction of the ladybug's total acceleration? And let's try this. Won't let me do this meeting control as a... All right, let me stop the share for 1 second. Try doing a poll, launch poll, share screen. Okay, so the question is, for this particular clicker question, what do you think? What is the direction at the moment shown of the ladybug's total acceleration? Give people 30 seconds. Do, 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 do. All right, we're going to pause in 5, 4, 3, 2, 1. Laura, I'll get to you in 1 second. And polling. Let's share this. So a majority, 47% say B. So let's look at this. So one, centripetal acceleration is always towards the center of the circular path. So in this case, since the ladybug, we're looking at it when it's right here. Let me go to a different color here, draw green. So my centripetal acceleration is going to point towards the center of the circular path, or my radial acceleration. But in this case, there's not traveling at a constant speed. The ladybug is slowing down. Keep in mind, tangential acceleration always points either in the same direction of the velocity, if it's speeding up, or opposite direction of the velocity, if it's slowing down. So the ladybug, the velocity is always tangent to the path. So at this point right here, the velocity of the ladybug points straight up. So if the ladybug is slowing down, the tangential acceleration is in the opposite direction. So what we have is my radial acceleration would be towards the center. Since it's slowing down, my tangential acceleration is in the opposite direction of the velocity. So my total acceleration is somewhere in the third quadrant. So the correct answer would be C. If it wasn't speeding up or slowing down, the answer would be B, because my radial acceleration would be the only acceleration I'm undergoing. But since I'm changing speed also, I also need to take into account tangential acceleration. All right, let me pause this for a second. Laura, did you answer my question? Can we use things from the 4A site lecture notes? So just in terms of the quiz or the celebration, once you start the celebration, there are no internet searches. So get everything you need, but no, technically, the only real caveat is no internet searches during the celebration. Okay.
I was actually going to ask about the clicker question.
Okay.
I don't know if it's the same for everyone, but on mobile, I couldn't see the question when the poll popped up.
Oh. Okay. These polls don't seem to be working very well. So yeah, I won't do any more polls for this, but I'm going to try and figure out how I can do clicker questions. Even me, sometimes I have trouble seeing the poll once I start it. So sorry about that. Okay, so chapter 8, again, big things for this chapter are uniform circular motion. So in terms of just some of the equations, we know that something moving in a circular path at a constant speed, the speed would be given by 2 pi r divided by the period. We know that radial acceleration points towards the center and is v squared divided by r. We pull up this chat. On phones, it pops up, you can go back and forth, just not full screen. Gotcha. Okay. Let's just quickly look at chapter 9. So chapter 9 was all about work and kinetic energy. If you remember in chapter 9, we weren't dealing with potential energies because we weren't dealing with interactions. So in this chapter, big thing is our basic energy model. I've spent a bunch of time on that. Basically, there's a system that you define. Anything that's not part of the system is the environment. Any forces the environment exerts on the system is an external force which changes the overall energy of the system. Within a system, energy can be interchanged from one form to another, but the total amount of energy in a system doesn't change unless something from outside the system is doing work on it. We looked at kinetic energy, work done by a constant force, dot product, work done by a varying force. So just real quick summarizing it, we know kinetic energy is energy of motion, and it's 1/2 the mass of the object in kilogram times the speed in meters per second squared. It is a scalar, which means you cannot break kinetic energy up into x and y components. Work done by any force, I could always write as the integral of f dx from some initial to some final position. If we're talking about one dimension, the integral of fx dx. That always applies. But if the force is constant, we can write the force as the dot product of the force dotted into the displacement, which is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. A couple things about work. If a force does positive work, that force is adding energy to the system. If a force does negative work, that force is removing energy. And big thing is, if the angle between the force and the displacement is 90 degrees, then that particular force does not do any work. This is important to know because sometimes the normal force and gravity end up not doing work in a system because, let's say, the object is moving horizontally, the normal force acts straight up, gravity acts straight down, angle between the normal force and the displacement would be 90. Couple other things. Let me just say power. Power is going to be important in physics 4B, but I didn't cover it in that much detail. In terms of things to not focus on for this celebration, don't worry about power. But in terms of thermal energy, the one equation we have is how much thermal energy changes. And that's the force of kinetic friction times the displacement over which kinetic friction acts. So just going through some of the important things. So like I said, change in energy of a system is equal to how much work is done on the system by external forces. And in chapter 9, we weren't dealing with potential energy. So the only forms of energy we were looking at are kinetic energy and thermal energy. Again, thermal energy, we only have an equation which gives us how much thermal energy changes. And we have these different equations for work. In this chapter, the other thing we looked at were Hooke's law, which is the force exerted on by a spring when the spring is stretched or compressed, and the dot product. Keep in mind, two different ways of getting a dot product. Magnitude of one vector times the magnitude of the second vector times the cosine of the angle between them. Or if you're given x and y and z components, ax bx plus ay by plus az bz. And in this chapter, we also looked at the work done by gravity, which is some reason not on this. Okay, so I don't see it on here, but the work done by gravity ends up being equal to negative mg times delta y. And the big thing about gravity, we'll get to this in chapter 10, but it's a conservative force, which means all that matters is where I started, where I finished. That's quickly chapter 9. Let me just touch on 10 and 11. Just for 1 second. Stop the share. I'm going to mute everybody. Start the share again. Okay. Oops, what happened there? Sorry, stop that. Share screen again. Okay, chapter 10. Basically, interactions and potential energy. So again, we kind of went through the energy principle. I talked a little bit about conservative and non-conservative forces. Easy thing to think about. You're only going to see two conservative forces in physics 4A. You've seen them already. Gravity and the elastic force from a stretched or compressed spring. Every other force is non-conservative. Big thing about conservative forces is you can define a potential energy. And the way we define potential energy is we don't define the potential energy, but we define how much the potential energy changes for a conservative force as being negative the work done by that conservative force. From that, what I found or derived for you was that gravitational potential energy is given by mgy, elastic potential energy 1/2 k times delta x squared. For gravitational potential energy, you can define y equals 0 anywhere. So in general, there's going to be two logical places to usually define y equals 0, either where the object is starting or where it's finishing. Energy bar charts, don't worry about. Energy diagrams, don't worry about. Force and potential energy, don't worry about. Big thing from this chapter is really just conservation of energy. And let me remind you, our big giant equation that pretty much always applies is the work done by all external forces plus the initial kinetic energy plus the initial gravitational potential energy plus the initial elastic potential energy equals my final kinetic plus my final gravitational potential plus my final elastic potential plus any change in thermal energy. Couple things to keep in mind. Potential energy is always an interaction between two objects. A single object cannot have potential energy. So if I want to use gravitational potential energy, the Earth has to be part of my system. If I want to use elastic potential energy, the spring has to be part of my system. And if I want to use thermal energy, all objects whose temperature changes has to be part of the system. And really, this is sort of the one equation that pretty much all of chapter 10 depends upon. In essence, what you're doing is defining your system, looking at if there's external forces doing work on the system, and then just looking at some initial condition, some final condition, making sure we have all of the relevant energies, and then solving for the unknown quantity. So again, in this case, don't worry about energy bar charts. Don't worry about energy diagrams. Like I said, the big things are gravitational potential energy, mgy, elastic potential energy, 1/2 k delta s squared. And then last but not least, just in terms of the material, chapter 11 was all about impulse and momentum. Things that we covered that are relevant for this celebration. What is impulse and momentum? We looked at the impulse momentum theorem. Basically says the impulse on an object, which is equal to the integral of the force with respect to time. Keep in mind, work is the integral of f dx. Impulse is the integral of f dt. So this is from some initial time to some final time, which is also equal to the average force times delta t. The impulse on an object equals the change in momentum of the object, which if we're talking about the x would be the final momentum in the x minus the initial momentum in the x. If you were given a curve of force versus time, the impulse is also the area under the curve. Conservation of linear momentum. So again, with momentum, it's not looking at the work done on the system. Conservation of momentum says if the sum of the external forces on a system is equal to 0, then the final momentum of that system equals the initial momentum. Momentum is not changing. And the momentum of a system is the sum of the momentum of all the objects in the system. Two things you don't need to really worry about mathematically. So one, an inelastic collision is one in which the two objects, well, inelastic collision is one in which kinetic energy is not conserved. An elastic collision, a perfectly elastic collision, is one in which they are conserved. Generally, if we're looking at a collision, oftentimes the objects will stick together after the collision and move as one. We call that a perfectly inelastic collision. I am not going to deal in this celebration with perfectly elastic collisions. There are a couple problems in the homework. Anything dealing with an elastic collision, I'm not covering that mathematically. It's just a couple equations in the book that you could look up. And in terms of momentum in 2 dimensions, you only need to look at this conceptually. And I'll do an example problem. But basically, momentum is conserved. And if I want to look at a collision that's not one-dimensional, so like let's say I had an object that was at rest and another object was moving and those collided, and after the collision, they moved off at angles. What I would look at is say the momentum in the x direction is conserved, the momentum in the y direction is conserved, and I would end up with 2 equations with 2 unknowns that I would use to solve, let's say, to get the final velocity of one of the objects. I'm not going to ask you to do that. So big things from this chapter 11 are total momentum of a system. Well, one, momentum we know is just mass times velocity. And the total momentum of a system is just the sum of the momentum of all the objects in the system. And impulse is the area under the curve of force versus time. Don't worry about momentum bar charts. Don't worry about collisions in 2 dimensions mathematically. Don't worry about rockets. And then in terms of collisions, just sort of understand conceptually what's the difference between an elastic and an inelastic. Inelastic kinetic energy is not conserved. Elastic kinetic energy is conserved. And then perfectly inelastic is when they stick together and move as one afterwards. So let me pause that. What I want to do is just answer any questions about the kinds of material that may or may not be on it. And then if there's no more questions, I want to just do some sample problems of the type of material that you see in terms of the difficulty. Just to show you that the problems that you see on the celebration tomorrow, not going to be on the same order as the problems that you would see in celebration 1. They're going to be 1 or 2 steps max. So questions on anything that's not going to be on the celebration or things that I included that you need clarification on?
Hey, Joe.
Yeah.
Do we have to worry about explosions on the celebration?
So an explosion, I could ask you conceptually. So let's just do a quick share of a whiteboard. So, let's say that, again, you just had this object that's in space and it's at rest. So this object's not moving, which means it has no momentum. So if I define my system as just this object, whatever caused the explosion is an internal force, which means the momentum of the system is not going to change. So if this thing is at rest, then that means initially it has no momentum, but this is true in both the x direction and the y direction, which means after the explosion, the total momentum in the x direction still has to be 0. The total momentum in the y direction still has to be 0. So I could ask like a conceptual question and say, okay, after the explosion, if I have 3 equal mass pieces that result from this explosion, and I give you what is the velocity direction of 2 of these pieces, you should be able to, just from conservation of momentum, think about, well, if the momentum still has to be 0 after the collision, what is the direction that the third piece has to be moving? And in fact, just let me ask you a clicker question on that, just to give you an example. So clicker questions. That's not what I want to do. Okay, let's look at this 1110. So car 1 is traveling due north and car 2 is traveling due east. Oh, this isn't an explosion, but this is like the opposite of an explosion. So similar here, in case of something blowing apart, this is 2 things coming together in 2 dimensions. After the collision, 1 car rebounds due south. Which of the numbered arrows is the only one that can represent the final direction of car 2? So here's a case where if I model my system as these 2 cars, whatever kind of force they exert on each other is going to be an internal force. And here's a great, here's where momentum is so useful. Trying to model the collision between 2 cars using conservation of energy, unbelievably challenging. You've got the metal deforming, you've got heat being generated, you've got sound being generated. But even though energy is not conserved, momentum still is. So here, car 1 was traveling due north, car 2 was traveling to the east. The total momentum of the system, which is 2 cars together, if I were to just add these like vectors, my initial momentum combined is somewhere in the first quadrant. I'm not given the speeds or the masses, but I know that car 1 has a momentum pointing straight up, car 2 has a momentum pointing to the right. So the total momentum is somewhere in the first quadrant, which means even after the collision, if momentum is going to be conserved, it still has to have the same direction, the same magnitude as before the collision. So if we're told car 1 rebounds due south, so wait, this was car 1 beforehand, this was car 2 afterwards. If car 1 rebounds due south afterwards, what is the only possible direction for car 2? Well, if the final momentum of the combined system is still going to point in the first quadrant, then car 2 is going to have a x component pointing to the right. It's going to have a y component pointing straight up. The final momentum of car 2 is still going to have to be, well, it's going to have to be somewhere in the second quadrant so that the final momentum of the system still points in the same direction it did before. So it's not 2, that would be 4. So that may have been a long-winded response to your question, but explosions is just saying that if something's at rest to begin with, after the explosion, the total momentum still has to be 0. So when I add up the momentum of all the little pieces it explodes into and add them like vectors, it's still going to be the same as it was before the explosion. Okay, can we navigate back and forth in our exam, or once we answer question 1, can we not change the answer? Ooh. As somebody who's taken the quiz before, I don't remember whether or not you can go back and change your answers.
I don't think you can.
Yeah, I don't think you can either. That was my thought. Can't change it, don't lock it in. Yeah, so once you submit an answer, then that answer is submitted. You can't go back and change it. So just a couple things, like I said, 25 multiple choice problem questions. The problems are relatively straightforward. Take your time, right? 3 hours is more than enough time. And in fact, this Mastering Physics software, just to let you know, shows you the average time that anyone who's ever used this software has taken to do the problems. And out of all 25 problems, the mean time from everybody who's taken these problems on Mastering Physics is about 75 minutes. So I'm giving you a full 180 minutes. Even if you work really slowly, it should be plenty of time. So get organized, you know, sit down, make sure you don't have any distractions for 3 hours, and then just go through methodically, question by question. So let me just actually show you now. Let's go through a couple things. So one, let me just show you that in Mastering Physics, I created a short little practice quiz. It's not really a quiz, it's just some questions. And those are the ones I'm going to go through right now. So this is sample questions for Celebration 2. I just had this sort of as a review. You don't have to do it, but it's going to give you an idea of the kinds of questions that I'm going to ask. And what I did is I just uploaded this into OneNote. So let's just kind of go through some of the problems just to give you an idea of the level of the problems. So here's a problem from chapter 8. And again, this is not on the Celebration, but this is the kind of problem you might see in terms of the difficulty. So a car enters a 300-meter radius horizontal curve on a rainy day when the coefficient of static friction between the tires and the road is 0.6. What is the maximum speed at which the car can travel around the curve without sliding? So, you know, let's say this is a bird's eye view. You're looking at above. This car is taking a turn, and we know the radius of the turn is 300 meters. And again, if I were to draw a free body diagram of the forces acting on this car, and again, this is a free body diagram, I guess, looking from the above. Anyway, looking from ground level, I have basically the normal force acting straight up. I've got gravity, mg, acting straight down. And the force that's keeping the object moving in a circular path. In this case, it's the friction between the tires and the road that's keeping the car moving in a circular path. So static friction is the only force responsible for keeping this in a circular path. So if I were to define my positive x to the left, so one, I highly recommend always defining positive in the direction of the acceleration, especially if we're talking about centripetal acceleration. So then I know that my acceleration is v squared over r to the left. So if I do the sum of the forces in the x direction equals max, what I would get is the force of static friction has to equal mv squared over r. Now we want the maximum speed this car can travel without sliding, which means that static friction has reached its maximum value, right? If I go any faster, that's going to slip. So if I want the fastest I can move without slipping, I want to know what speed it's going when static friction has reached its maximum value. Hopefully you recall the maximum value of static friction is given by μs times the normal force. And in this case, where the only two forces acting vertically are the normal force and gravity, those are going to be the same. So the normal force will be equal to mg. So what you would get is the force of static friction times mg equals mv squared over r. And then I can just solve this equation for v. So here's a case where relatively simple problem in terms of the overall setup. At most, it's going to be 1 or 2 steps. Why is it static if the car is not moving? Good question. Static friction and kinetic friction for a tire, kinetic friction would be if the tires lock and then the rubber is actually sliding across the road. So if you have like skid marks, that would be because of kinetic friction where the tire is actually sliding across the road. In terms of driving, it ends up that as the car is sort of rolling over, there is no slipping between the road and the tire. The tire's not sliding across the road, so it ends up being static friction. Rolling friction. So here's a case where, actually, it would probably be rolling friction now that I think about it. All right, let me not ask a question like that on celebration. I'll make sure. All right, let me do why can't I sample question? Let me just do a couple more problems just in terms of giving you an idea of the overall level of the kinds of problems. And I may not solve everyone just because I want to set up the math, and then algebra is just straightforward. Problem 917. An object is acted upon by a force that's represented by the force versus position graph in the figure. What is the work done as the object moves from 4 to 6 meters? What is the work done as the object moves from 6 to 12 meters? So I think out of your 25 questions, I'd have to look, I want to say maybe 15 or 17 of them are multiple choice. Some of the problems you actually have to input the answers. So one, keep in mind in terms of significant figures, I would say if you give your answers to 2 or 3 significant figures, you should always be pretty safe. So here, if I want to know what is the work done from 4 to 6 meters, work is always the area under the curve of force versus position. So if I wanted to know the work done, in this case, between 4 and 6 meters, it's the area under the curve. This is a rectangle with a height of 10 newtons, a width of 2 seconds. That's how I end up with my answer of my work being 10 newtons times, I'm sorry, did I say 2 seconds? 2 meters. I end up with 20 joules or 20 Newton meters. And then if I was looking at the work from 6 to 12 meters, again, in this case, then it would just be the area of this triangle. And again, I'll let you do that. You can find that it ends up being 30 joules. One thing to keep in mind in terms of work, if I have some area under the curve, so let's say this is the force in newtons versus the position in meters. You know, I could have some force that goes negative for a while. So if I'm calculating the area under the curve, let's just say the total area of this. One, any area above the axis is going to be positive, below is going to be negative. So like if I wanted the total work done by this force, I would break this up into a rectangle, a triangle, and then another triangle and a rectangle. Just keeping in mind that when you're below the axis, the work done is going to be negative. In terms of some conceptual questions, some of the conceptual questions will have a little bit of sort of algebra problem solving in it. So let's look at conceptual question 910. A 4 kilogram object is moving with a speed of 2 meters per second. A 1 kilogram object is moving at a speed of 4 meters per second. Both objects encounter the same braking force and are brought to rest. Which object travels the greatest distance before stopping? So both of these objects are moving. They have some initial kinetic energy. They're both going to be brought to rest by some braking force. What I know is that the work done, so one, what are these objects? Are these cars? Anyway, the change in kinetic energy of the cars is going to come from the work done on them by the braking force. So what I could say is the work done by this braking force equals the change in kinetic energy, which is the final kinetic energy minus the initial. They both end up at rest, so they both have a final kinetic energy of 0. So the work done by this braking force is going to be equal to negative the initial kinetic energy, right? This force of friction is removing the kinetic energy from the system, converting it into thermal energy. Now, in this case, I'm not defining my systems to sort of include the road. So what I would say is the work done by friction is converting some of the kinetic energy and removing it from the system. If I included the surface as part of the system, then I would say that there's no external forces and that some of the kinetic energy is being transformed into thermal energy. But in this case, friction's doing negative work. It's removing energy from the system, resulting in the cars losing kinetic energy. Here's the key point. They have the same braking force. So if I just imagine that braking, the work done is going to be the force, and let's just say the force of friction times the displacement times the cosine of 180. And that's going to equal 1/2 m times v initial squared. Key point to this problem is they both start off with the exact same kinetic energy. For the first one, I have a 4 kilogram object moving at 2 meters per second. So its kinetic energy is 1/2 times 4 kilograms times 2 meters per second squared. So I have 2 times 4. This gives me 8 joules. Second one, I have a mass of 1 kilogram moving at 4 meters per second. Its kinetic energy would be 1/2 times 1 kilogram times 4 meters per second squared. I end up with the exact same kinetic energy to begin with. So since they started with the exact same kinetic energy and they end with the exact same kinetic energy, which is 0, that means the work done by this braking force is the same on both. And since we apply the same force, that means it must act over the exact same distance. So the correct answer was both objects travel the same distance. Okay, let's do a couple more and then I'll pause and see if there's any questions. Let's do a problem that requires a step or two. So problem, which one is this? 1028. And just so you know, if you go and do these, I took a lot of these from a different book. So the problems 1028 have nothing to do with your book. An object of mass 4 kilograms starts at rest from the top of an inclined surfaceless inclined plane of height 10 meters, shown in the figure. If the speed of the object at the bottom of the incline is 10 meters per second, how much work does friction do on this object as it slides down? So here, when this thing reaches the bottom, the speed is 10 meters per second. So one, this could be a cool little question I could ask. If something starts at this height of 10 meters, slides down and reaches a speed of 10 meters per second at the bottom, is there friction? And the way you would figure this out is, does the kinetic energy of the mass at the bottom equal the potential energy at the top? Here you'll see that that's not the case. So how would I set this problem up? Any energy problems, first thing I would do, define my system. So in this case, if I define my system as, what is this? Hey, it's an object. What do you know? An object plus the Earth. I'm including the Earth as my system so I can use gravitational potential energy. So one, what's happening here conceptually? The object starts with some gravitational potential energy. As it's sliding down, that potential energy is getting converted, some of it to kinetic energy, but friction is doing negative work, which is removing energy from the system. So if I want to know how much work does it do, what I can say is the work done by all external forces plus my initial kinetic energy plus my initial gravitational potential energy equals my final kinetic energy, that's initial there, plus my final gravitational potential energy. And here, I'm not including the ramp as part of my system. I'm not looking at thermal energy being generated. What I'm looking at is how much work does friction do. So in terms of the external forces acting on this box are the normal force and the force of kinetic friction in this case. The normal force is not doing any work because the object's sliding down the incline, the normal force is perpendicular to it. So the only work done is the work done by friction. So this work done by external forces is equal to the work done by friction. The object started from rest, so it has no kinetic energy. And one thing I didn't do is I didn't define my y equals 0. So here I'm going to define y equals 0 at the very bottom, which means this thing starts off with no kinetic energy. It ends with no gravitational potential energy, but it is moving. So my initial gravitational potential energy is just going to be my mgy initial. So what I get here is basically the work done by kinetic friction plus the initial gravitational potential energy equals my final kinetic energy. Or the work done by kinetic friction is 1/2 mv final squared minus mg y initial. So again, relatively straightforward in terms of the actual problem solving. At most, you might have 2 or 3 relatively easy steps, but here's a case where the object started with gravitational potential energy. There was friction, which was removing energy from the system. So not all of that gravitational potential energy all got converted into kinetic. Okay, let's do one more conceptual question, and then I'll answer any questions. So here's a conceptual question. As a tile falls from the roof of a building to the ground, its momentum is conserved. True or false? Well, one, momentum, keep in mind, is mass times velocity. So as the object is falling, it's increasing its speed, so its velocity is increasing, so its momentum is increasing. So if I'm looking at my system as just the tile, the Earth is an external force which is exerting an impulse, which is causing the momentum of this tile to change. Now, if I was specific and said for my system, if instead I said the system was the tile and the Earth, and this says as the tile falls, it's the momentum, well, if instead I said the momentum of the Earth and tile is conserved, that would be true. Because if my system is the Earth and the tile, any forces they exert on each other are internal forces which aren't affecting the overall momentum of the system. So this is kind of like Newton's third law. As the ball is falling, technically the Earth is moving up to meet the ball. And if I dropped an object from rest, it has no initial potential or no initial momentum. What that means is if my system is the Earth and the ball, the momentum would remain 0, which means as the ball moves down towards the Earth would be moving up towards the ball with the exact same magnitude momentum. All right, let me pause this, take a look at comments. Is this OneNote up on your website? So I do not have this OneNote posted. I literally just created it late last night. I will post that today. If the system was not included, how do you know? So here I wanted to mention this also, the way this question was worded, I would have been specific. So let me just share this again. Share screen. So I made sure that the questions being asked on the celebration were pretty clear. I chose this actually just so I could talk about the definition of the system, but like here, it just says as a tile falls, its momentum. So they're being specific that we're only talking about the tile. So in that case, its momentum is not conserved. If this question said the momentum of the Earth and tile are conserved, that would be true. Okay, stop that. Other questions I can answer from anybody?
Yeah, I have a question from the Chapter 11 homework.
Okay.
I don't remember which problem it was, but basically it's a golf ball is dropped from a height of 2.2 meters. And they give us a graph, and they're asking us basically what's F max.
Oh, I'm trying to think what's the easiest way. Hold on. Physics 4A, homework assignments, individual chapters, chapter, which one? 11? I believe they give you
The problem after 11.
problem 41. All right, let me share this for share screen, individual chapters. Okay, is it this one? 41? 200 gram, yeah. A 200 gram ball is dropped from a height of 2 meters, bounces on a hard floor, rebounds to a height of 1.5 meters. What is the maximum force? Robert, is that one? Can you see it?
Yeah, that's the one. Yep.
Okay, so let me share screen. So one, let me just say this particular problem is harder than I would ask on the celebration. But what you were told was this object is dropped from a height of 2 meters, hits the floor, and then bounces up to a height of only 1.5 meters. Is that right?
Yeah, more or less. I have different numbers, but that's okay.
Let me just double check real quick. 2 meters. Okay, so yeah, so if you're doing this on mastering physics, it's randomizing the variables. But here's what you're doing is one, you're going to use conservation of energy to figure out how fast is the ball going right before it hits, how fast is it going right after it hits. So right before it hits, it's got some velocity initial, which is moving straight down. And then right after it hits, it has some velocity final, which is moving straight up. You would use conservation of energy to figure those out. Basically, what you're saying is...
Oh, shit! Oh, shit!
All right, mute everybody.
Yeah, but
Please be aware if you are attending this that, yeah, we can hear you if you unmute us. Okay, so going back to this. So one, you would use conservation of energy to figure out how fast something's going after it fell 2 meters. What you would basically get is mg y initial equals 1/2 mv squared. So what you could get is the speed that it's going to hit with ends up being equal to 2g y initial. And then I could also say that how high this thing goes, if it went 1.5 meters, I could also use this same equation to figure out how fast it must have been going. So you use conservation of energy to figure out the velocity right before it hits, the velocity right after it hits. So what I have is basically m times v final after the collision minus m times v initial. And I get these from conservation of energy. Well, I know that impulse equals the change in momentum. And the impulse I can get from the area under the curve. So I forget exactly what this thing looks like, but it was like I think a triangle, right? Where I had F max was up at the top, and they gave us what this delta t was. Well, since this is a triangle, the area under the curve is just 1/2 base times height. So I know that the area of this is going to be 1/2 times F max times delta t. So this is the area under the curve, which is the impulse. Impulse equals change in momentum. And so once I figure out the velocities right before and after it hits the floor, I can figure out how much the momentum changes. So then I can solve that equation for the impulse, which is the area under the curve, equals m times v final minus v initial. But again, don't worry about this problem is more advanced than I would do for the celebration. But if you were given a curve of force versus time, you should be able to get the impulse by getting the area under the curve. Or if I gave you the initial and final velocities, then you would be able to do this problem in just 1 or 2 quick steps, not having to use conservation of energy to first get the velocities. All right.
So even though this was in like the conservation of momentum chapter, this was more of a conservation of energy.
Well, it was a two-step problem. It was, well, yeah, using conservation of energy to get the speeds. And then once I know the speeds, then I can figure out what the velocities are so I can get the change in momentum and relate that to the impulse. So yeah, one of the tough things too is, you know, physics builds upon itself, and the final celebration would have had 3 or 4 problems that took Newton's laws and kinematics and, you know, momentum and combined them. But just given the realities of this new situation, the problems are going to be more straightforward using 1 or 2 steps at most. So that said, you will still need to use some Newton's laws in this celebration, right? You may need to figure out what is the tension first before you can figure out the work done by tension, something like that. So I'm not going to ask you to use kinematics in terms of memorizing the equations of constant acceleration, but you will still need to remember Newton's second law, because you may need that for a couple problems. Chapter 11 due. So just so you know, I wanted to post chapter 11 just so it's up online. I am not collecting chapter 11 through Mastering Physics. So if you want to input that, you can do that to sort of check your work. But no, I am not collecting chapter 11 in terms of a graded homework assignment. All right, so I want to just sort of, I missed a memo. Where do I find PLC 11? Oh, maybe I never, I don't remember if I think I attached it to your email, but I did upload course home, Physics Joe McCullough's homepage. So just so you know, your PLCs, oh, apparently I did not upload it yet. I will email it out right now along with the old celebrations that I had. Well, I'll email it out in 15 minutes. So yeah, totally sorry. I completely spaced to upload that, but I think I did email it out. If not, in essence, it's a 1-page cheat sheet for tomorrow's celebration. All right, so the official lecture portion of today's Zoom, done. Bringing in office hours, if there are any. I'm gonna hang around for another 13 minutes. Thank you, everybody. I'm gonna hang around for 13 minutes and answer questions if anybody has any. Thank you to everybody who joined. Good luck tomorrow. Hopefully that everybody does pretty well. It should be relatively straightforward. Like I said, 3 hours from the time you click start should be more than enough time. Just breathe, make sure you read everything, think about it. I think people should do fairly well. Thank you, Laura. Thank you, Charlie. Thank you, Grant. Thank you, everybody.
Joe?
Who's got a question? Rosa.
Yes. Do you hear me?
I can.
Okay. I have a question about mechanical energy.
Okay.
Can you explain like very quick, like
Yeah, mechanical energy really simply is just the name we give to kinetic plus potential. So mechanical energy, we often just write as E mech, but it just equals the kinetic energy of an object plus all forms of gravitational potential energy. So it doesn't include thermal energy, it doesn't include chemical energy. So mechanical energy, kinetic plus potential. And what we know is that if the work done by all external forces equals 0 and no friction. If there's no friction, then there's going to be no thermal energy generated. If this is true, then what I can say is my final mechanical energy equals my initial mechanical energy. In essence, remember, our big equation is the work done by all external forces plus my initial kinetic energy plus my initial gravitational potential plus my initial elastic potential equals my final kinetic plus my final gravitational potential plus my final elastic potential plus any thermal energy generated. Draw, I want to format blue. So if no external forces are doing work and there is no friction, so there's no thermal energy generated, then basically the sum of kinetic plus potential is not changing. We call this sum just mechanical energy. So if there's no work done by outside outside forces, if there's no frictional forces removing energy as heat, then the total kinetic plus potential is going to equal the final kinetic plus potential.
Okay, thank you. I have one more question. Do you have the answers for the last quiz, the quiz 10?
Oh,
I think
I do. And one thing I did forget to show people was that on your online resources page, open link new tab. I did post these solutions to the last 3 quizzes from Mastering Physics. So chapters 8, 9, and 10, if you click on this, it'll show you the quiz questions along with the solutions, or at least along with the right answers.
okay, can you explain a question? That one when we have to mechanical energy. I think it was it was just I think not the last one. I think it's that one.
This one?
Yes, just part A, because I think I missed like 30.
A roller coaster of mass 80 kilograms is moving at a speed of 20 meters per second. At point A, the vertical height above the ground is 200 meters. What is the total mechanical energy of the roller coaster? So in this case, one, there's no spring. So I don't need to consider springs, potential energy. Can I write on this? I can't. So we've got a mass of 80 kilograms at a height of 200 meters moving 20 meters per second. Let me just jot those down real quick. So we've got the mass is 80, speed is 20, height is 200 meters. All right, so new share. So if there's no spring, then my total mechanical energy is just going to be my gravitational potential energy plus my kinetic energy. If there was a spring, then I would need to also look at elastic potential energy. So in this case, we were just given that the mass was 80 kilograms, the initial height was 200 meters, and the speed was 20 meters per second. So if I want to get my total mechanical energy, it's my kinetic energy, 1/2 times 80 kilograms times 20 meters per second squared, plus my gravitational potential energy, 80 kilograms times 9.8 meters per second squared times 200 meters. So if there's no air resistance, no friction, that total mechanical energy is not going to change. So like as this roller coaster is moving up and down the hills, so here it started off at a certain height of 200 meters and it was moving. So it had both gravitational potential energy and kinetic. That total amount of energy is not going to ever change. As this object is moving down, it's increasing in speed, so its kinetic energy is increasing, but it's decreasing in elevation, so its gravitational potential energy is decreasing, but the sum of those two is not going to change. Does that answer your question, Rosa?
Yes, thank you.
You're welcome. Anybody else? Any other questions I can answer? Could you explain the clicker question once more with the ladybug one? Yeah, let me do that real quick. Share screen again, and let me just make up a different one. Clear drawings. So let's say I've got an object which is moving. What is this? This is clockwise, right? I always have to think about a clock. And let's say the object is right here, which means that I know the velocity points to the left. And I want to know what is the direction of the total acceleration. Well, we have two different accelerations we can look at. Radial acceleration, keep in mind this has to do with a change of direction. It doesn't matter whether an object is speeding up, slowing down, or moving at a constant speed. If it's turning, there is an acceleration related to the direction changing. This is always towards the center of the circular path. I also have a tangential acceleration. That's related to a change of speed. And again, this radial is a change in direction. So let's just say that this object was moving in a circular path at a constant speed. Well, one, regardless of whether the speed is constant or not, the fact that it is moving in a circular path means it has a radial acceleration towards the center. So right now, it has an acceleration. So I'm looking at it when it's at the bottom. Like when it's right here, again, the velocity is always tangent. My acceleration for change of direction is always towards the center. But if the speed is changing, then there's also another component of the acceleration called tangential acceleration. And that's either going to point in the same direction as v, if it's speeding up, or the opposite direction of the velocity, if it's slowing down. So let's take a look at, do this in red. Let's take a look at this position right here. And let's just say the object was speeding up. Ew, I do not like that color at all. So again, I'm looking at it right here and the object's speeding up. Well, it has a radial acceleration towards the center, and the fact that it's speeding up means my acceleration tangentially points in the same direction as the velocity. So my tangential acceleration, if I'm assuming it's speeding up, is pointing in this direction. So we don't have enough information to get any exact angles, but I know something that's pointing to the left in terms of the x component, pointing straight up. This would have a total acceleration that would point somewhere in the second quadrant. Now let's look at the other case where it's up here. Again, velocity is always tangent to the path. So in this case, the velocity would point straight up. So if the speed is changing, if it's speeding up, tangential acceleration would point straight up. If it was slowing down, the tangential acceleration would be pointing opposite. So let's just assume in this case that the object is now slowing down. So now again, it's changing directions. So the radial acceleration is pointing towards the center, but now it's slowing down, which means my tangential acceleration is in the opposite direction of my velocity. So my tangential acceleration would be straight down. So in this case, I have something that points to the right in terms of the x component, points straight down in terms of the y component. My total acceleration would be somewhere in the fourth quadrant. All right, let me stop that for a second. So total A would be fourth quadrant for, yep, in that case.
Can we go over the last problem in the chapter 10 quiz?
Last problem on chapter 10 quiz. All right, how am I going to access that again? Course home, is that it? Chapter 10 quiz. Am I sharing this one? Can you guys see this?
Yes,
Yes.
we can see it.
Oh, you want to look at problem 1014?
Yes.
A 60-kilogram person drops from rest to a distance of 1.2 meters. Ideal spring, the platform drops 1.2, and then another 1.2 meters, then 6 centimeters. What is the spring constant of the spring?
Hey, Joe, if you use snip, you could go ahead and snip that and then be able to write directly on it.
If I use snip.
Yeah.
What do you mean snip?
It's one of the Windows programs.
Just to cut and paste it somewhere?
Yeah.
Oh, actually, anyway, I'll figure that out later. I just
Okay.
I need to answer this real quick because my daughter's coming. All right, so stop the share. Let's open up a whiteboard. Clear all drawings. So my understanding is I've got a, having technical difficulties. Hold on. Share screen. Whiteboard. So I have an object which is, am I getting this right? The mass is 60 kilograms and it's 1.2 meters above a spring. And then we drop it and the spring, what does it say, compresses by another 6 centimeters? Does that sound right?
Yes, that sounds right.
Okay, so here I would define my system, and I don't remember what this is, but let's just say as the mass, the Earth, and the spring. And what I'm going to do is I'm going to define y equals 0 to be when the spring is compressed the most that it is. And so my initial height is going to be 1.26 meters. My final height is going to be 0. So if I include as my system the mass, the Earth, and the spring, then what I could say is there are no external forces doing work. There's no air resistance, there's no friction, so there's going to be no thermal energy generated. So what I can say is my initial kinetic energy plus my initial gravitational potential energy plus my initial elastic potential energy equals my final kinetic plus my final gravitational potential plus my final elastic potential. So the question for you is, how many of these 6 terms survive? How many of them are not 0?
2. 2 survive.
2 survive.
The UG
Hold
initial.
on, hold on, 1 second. Hello? Oh. Hold on 1 second.
I think the spring, and no, sorry, the kinetic initial survives and the spring final survives.
Okay. Sorry about that. My daughter's here. I have to end this in like 2 minutes. So if I look, this thing started from rest. So my initial kinetic energy was 0. It ended at rest. So my final kinetic energy was 0. I have to run downstairs. The spring is initially not compressed, so it has no elastic potential energy to begin with. And I defined y equals 0 to be when the spring is fully compressed, so it has no final gravitational potential energy. So what I end up with is the initial gravitational potential energy of the mass equals the final elastic potential energy stored in the spring. Well, I know M, I know G, I know Y initial. Actually, what are we trying to find here? Was it the spring constant?
Yeah, we're trying to find K.
Okay, so this delta X is just going to be negative 0.06 meters or 0.6 meters. My Y initial is going to be 1.26 meters. I've got my mass. Basically, I'm just solving this equation for K.
Okay, thank you.
You are welcome. Sorry, I have to end this now. Good
Mhm.
luck. I will send out an email and a little bit with PLC number 11 and then some other information. Whew.
Okay.
All right, office hours done. Have a wonderful day, everybody. And yeah, good luck in the celebration tomorrow.
Thanks.
Thank you.
Have a good day.
All right, you two take care.